All right, so now we are going to move from concepts only to using those concepts to solve problems. So let's take a look at how you solve problems using Newton's laws of motion. Okay, and before we begin this first problem, again, it's a very, very good idea to have a list of all of those equations so that you can easily refer back to them and select the equations that are most appropriate for any given problem. Okay, so first up, we have the net force acting on an airplane. And that force has a magnitude of 1900 newtons and points in the positive x direction. Okay, so we know that it points in the positive x direction. That's how I'm going to set my coordinate system. The y would be like this, but we don't really care about that right now. If the plane has a mass of 860 kilograms, what is its acceleration? Well, we are only given information about an x component, so this one will be very, very simple. Let's just take Newton's second law, which is F equals ma, and plug in the information we know. Well, we know that this is 1900 newtons, and we know that the mass of the plane is 860. So all we have to do is solve for A. And when you solve for A and report it to the correct number of significant figures, you'll find your answer to be 2.2 meters per second squared. Okay, so that one, not bad. We only have motion in the x direction, so that makes this quite easy to solve. Okay, let's take a look at the next problem. Oh, this one has a lot more words. Now, this time we have three people, Mo, Larry, and Curly, who are pushing on a boat that is next to a dock. Each of them is exerting a force. That force is equal for all three. And that force is parallel to the dock. So we want to find the acceleration of the boat if they're all pushing in the same direction. And then we want to know what happens if Larry and Curly start pushing in the opposite direction from Mo. So let's just start with the first part, part A. Okay. So I know that I have three forces and they're all going, we're just going to say in the x direction. And I'm choosing the positive x direction because I see up here that I have a positive force. So I have three of them. Those arrows are obviously not the same size, but I tried my best to make them the same size. So each of these has a force of 80.5 newtons. And we know that the total mass is 752 kilograms. Okay, so again, just like the previous problem, this first part is pretty straightforward because we only have motion going in the x direction. So let's take that second law, F equals ma, and just plug in what we know. Okay, so don't forget that this is actually the sum of all the forces, which is equal to the mass times the acceleration. And in this case, we have the same force three times. So I'm just going to say 3F equals mass times acceleration. So that would be 3 multiplied by 80.5 equals 752 kilograms times the acceleration. And when you solve for acceleration and report your answer to the correct number of significant figures, you find that acceleration is equal to 0.321 meters per second squared. Okay, now I want y'all to try part B. Let's see what happens if we change two of these forces to go in the opposite direction. So y'all take a moment to do that. All right, so for part B, we have one force still moving in this direction. However, the other two forces are now going in the opposite direction, like so. Okay, so we know that the force is still 80.5. So this one is 80.5. But these two are now opposite. So instead of being positive 80.5, these are negative 80.5 newtons because they're going in the opposite direction. So we're going to use the same formula, F equals ma, and again, we know this is a sum. So if we just add up these three forces, the 80.5 plus a negative 80.5 plus another negative 80.5, you're going to find that the sum of those forces is negative 80.5. Our mass has not changed. It stays at 752. And you should have solved for acceleration like this. So the acceleration will now be a negative value. It will be negative 0.107 meters per second squared. So in this case, we see that the boat will begin moving in this direction very slowly. Okay. Next problem. We are now going to look at a pitcher who's throwing a baseball, and it is accelerating from rest to a speed of around 90 miles per hour. And we want to find out the force exerted by the pitcher on the ball. Notice it says we're going to estimate the force. So bear with me here as I walk you through this problem. We have information for the mass. So we know that the mass is 0.15. We know that it is accelerating from rest, so it's going to start at 0. And again, from rest also means this is 0, and our initial position would also be 0. The final velocity is 90 miles per hour, and that is all the information we have. Now, before you go any further, you might notice that the velocity is in miles per hour, but we always want our velocity in meters per second. So using 1 mile equals 1609.3 meters, I want y'all to convert 90 miles per hour into meters per second. Pause the video and do that. Okay, so if you have converted this correctly, you should have found that this final velocity is actually about 40 meters per second. And if you need assistance with that, please post in the discussions or reach out to me. Okay, so we are going to need some kind of information here so that we can solve for force. Force is mass times acceleration, but we don't have the acceleration. We only know what our final velocity was. So we're going to have to use an equation of motion that allows us to solve for acceleration before moving forward. Okay, so looking at my list, I am going to choose the following equation. Oh, I'm sorry, that should not be a plus sign. The final velocity squared is equal to that initial velocity squared plus 2 times a times delta x. I'm selecting this, and I'm going to explain my reasoning, because we know the final velocity and we know the initial velocity. We need the acceleration. The only other issue here is this delta x. While we were not given delta x, this is information that we could estimate. Now, why would I choose something that lets me estimate delta x instead of estimating time? Well, when we're talking about throwing a baseball, the time is going to vary in a lot more ways than the distance the ball travels. So, from the time a pitcher has the ball in his hand to the time that it is released and actually thrown towards the batter, that distance is approximately the same for each pitcher. Obviously, there are slight variations in that, but it will be approximately 2 meters each time. So delta x is approximately 2 meters. Again, that time is going to vary greatly. Not greatly, but it will have more variations than delta x. So we're going to estimate delta x. Now that we have done that, this will be fairly straightforward. So this will go away because we know that the initial velocity was 0. We can plug in the 40 meters per second, get that squared. It's equal to 2 times a times delta x, which is 2 meters. So a equals sorry, I had to put this in a calculator. Okay. A is equal to 16. What am I doing? That is, I'm sorry. I forgot to do the last bit of math there. 400 meters per second squared. So now that we have A, we can just plug everything into F equals ma to find our force, to estimate the force. We're going to have 0.15 kg multiplied by 400 meters per second squared. And that will tell us that the force is equal to approximately 60 newtons. So that is our estimate for the force exerted by the pitcher on the ball. And I know that one was slightly more confusing because we were estimating instead of it providing that information. Okay. Now, we're going to go back to a very wordy problem, but it's actually not that bad. So we see that we have 2 groups of canoeists, people in canoes, in a lake. They briefly visit, and then some person in the first canoe is going to push on the second canoe with a force of 46 newtons in order to separate them. We know the mass of each canoe and the occupants. So the first thing we want to do is find the acceleration the push will give to each canoe. Okay. So we have our canoe number 1, and we end up with canoe number 2. And we know that someone in this canoe, in canoe number 1, and I'll use a different color, is going to exert a force on canoe number 2 that's equal to 46 newtons, which means, and remember, for every force, there's an equal but opposite force, that the second one will also have a force on canoe 1, but it'll be equal magnitude in the opposite direction. So negative 46 newtons in that direction. Well, since the boats were resting, and so we're just going to say that this is all happening in one direction, and we're just going to call this the x direction. So I'm going to pick another color, and here will be my little system. So we'll call this x and this y. Everything is happening along this x-axis, and that is fantastic. It's going to make this problem slightly easier to solve because we don't have to break it apart into components. So, again, F equals ma. And we're going to have to solve this separately. So the acceleration of the first canoe and the second canoe is going to be different. So let's do the first canoe. We want to find, well, we want F1 equals M1 and A1. So to find that, let's plug in all our information for that first canoe. Okay, the force on the first canoe is negative 46 newtons, and that is equal to the mass of the first canoe, which is 150 kilograms. We can solve for acceleration. When you do so, you are going to find that the acceleration is negative 0.31 meters per second squared, and that's if you're using sig figs correctly. So pause this and go ahead and calculate the force for the second canoe. Okay, that force for the second canoe, F2 equals M2A2, where F2 is going to equal 0.18 meters per second squared. Okay, we have found the forces, or I'm sorry, this should not say F2, this should say A2. We have found the accelerations for each canoe. Now, what is the separation of those canoes after 1.2 seconds of pushing? Okay, separation means we're looking for some X value. Since they started together, we can just say X, or I guess the initial X is going to just be 0. So I'm going to erase a little bit of what I have so I have more space here. And go ahead and take a look at those equations of motion and see what would help you to solve this. So again, we are looking for the separation of the canoes, so something involving X. And I'm going to show you what I have chosen. I have chosen X equals X naught plus V naught times T plus 1/2 AT squared. Now, why would I choose this? Well, we can simplify this. So since they begin just sitting in the middle of this lake, we can get rid of this because it's going to be 0. And since they're sitting, that initial velocity is also 0, and this will disappear. This leaves us with X equals 1/2 AT squared. Well, we just calculated acceleration, and the problem gave us time. So we can find the X value, the final position value for each of the canoes, and we're going to have to do it. So we're going to do this twice. So first of all, we have X1. So when you plug in for the first canoe, the acceleration and the time, you will find that X1, that initial position, or I'm sorry, that final position of X1 is negative 0.22 meters from where it started. That means it moved backwards in this direction. And for the second one, again, using this same formula, you will find that the second one is equal to 0.13 meters. Now, we're not quite done. We want to know what this is total. So how far they are away. That means we need the delta X. To find delta X, we're going to have X2 minus X1, which is 0.13 minus a negative 0.22. So our final answer is 0.35 meters. That would be their final distance apart and the answer to part B. Okay. Now for this next problem, we're going to switch gears a little bit, and this is going to be more of a concept problem. So let's imagine that you have two boxes. We're going to have a small one and a large one, okay? And they're in contact. The large one is heavy and the small one is light, and they are resting on the floor. We are going to push with a force on either box. It doesn't matter. We can push here or we can push on this larger one. It does not matter which one. We want to know if the contact force between the two boxes is going to be the same in both cases, larger when we push on the large box or larger when we push on the small box. So let's consider what it means when we have two boxes in contact. Because these are in contact and they are resting, the acceleration of box number 1 is equal to the acceleration of box number 2. Okay, well, let's apply that to F equals ma. Okay, so these boxes are resting, which means the net force on them is 0. But if we apply a force to either the first or the second box, what would happen? Okay, well, let's take a look. Since the accelerations are the same, we know that will have no effect. The acceleration won't affect our overall force. Let's go ahead and look at that first box, F1. So if I push on F2, on box 2, if I push here on box 2, then whatever force I'm using on box 2 is being transferred to box 1. That means to solve for this, we're going to use the mass of box 1, which we know is less than the mass of box 2, and the accelerations are the same. So this is going to give us some value, and let's compare it to box 2. When we're pushing over here on box 1, because they're in contact, the only force now affecting box 2 is the one from box 1. The A's are the same, so they're not going to affect anything. That means this is going to be dependent on mass. Well, because the mass of this second box is larger, F2 will be greater than F1. That means that the contact force between the two boxes is going to be larger when we push on the small box. Okay. And there is a problem in the book where you will actually apply numbers to that. Another one. This time, we have a sled being pulled across an ice surface. So here's our surface. I'm going to make our sled a little rectangle like this. It's being pulled across an ice surface. And the force acting on that sled has a magnitude of 6.20 newtons and points 35 degrees above the horizontal. Okay, so that means it's being pulled about 35 degrees above the horizontal. So there's theta. So if it's being pulled, I've got some person pulling it. There's my little stick figure. If the sled starts at rest, that means the initial position, initial velocity is all 0. Then how fast will it be moving after traveling after it's pulled for 1.15 seconds? Okay. We need to select a potential equation of motion. So let's consider what's happening here. This is at an angle, which means this force is going to have X and Y components. So we're going to have to do a little bit more here, maybe. But let's think about something. Even though it has X and Y components, are both the X and the Y components affecting the overall movement of the sled? No. So I'm going to make this my X-axis and this my Y. There's Y, there's X. Is this person pulling the sled up in the Y direction? No, the person is pulling the sled across an ice surface. So it is moving only in the X direction. So for this particular problem, we can only pay attention to Fx. And again, F equals ma, so we're only paying attention to the X component right now. And we can solve this. We have our mass, which is 4.60 kilograms. Ooh, we don't have the acceleration, but we have a way we can find it because we know theta. And I hope you remember from earlier that we can solve for an x or y component by using the sine or the cosine. And we are going to be using the cosine of 35. Oh, oh no, that's correct. Okay. So we'll use the magnitude of the force multiplied. So it's going to be 6.20 times the cosine of 35, and that will tell us the acceleration in the x direction only. When you solve for this, you should find that the force in the x direction is equal to 5.08 newtons. Okay, so we want to know how fast it's moving after being pulled for 1.15 seconds. So take a moment and see if you can identify the correct equation of motion that we would use to solve this problem. Okay, I just realized, and that's why I paused this, because I realized my math did not make sense here. I just realized I have combined two things that I should not have, and I completely skipped something, and I apologize for that. So this should say AX, and I'm just going to erase all of this information so I can not confuse you, because I realized that I definitely just confused you, and I confused myself. And if you ever see me make a mistake, just let me know and I will correct it. Or if you suspect I've made a mistake, please say something so that I can go back and check. Sometimes I confuse myself, especially when I'm working in this format. So let's take the magnitude of the force, which is 6.20 newtons. And to find that acceleration in the x direction, we'll use the cosine of theta, or the cosine of 35. So that acceleration in the x direction is just equal to 5.08 newtons. Now we will take that information and plug it into F equals ma. I'm sorry, not F equals ma. I am really struggling today, and I apologize for that. Into the correct equation of motion, and let's see if you chose the correct one. And there are multiple ways you can solve these, but this is just the way I am choosing to solve it. I have selected the velocity is equal to the initial velocity plus acceleration multiplied by time. And I chose that because we are solving for how fast it's moving. So we want to know the final velocity. Well, it started from rest, so this goes away to 0. And we have that the velocity is equal to a times t. We have both of those values, so 5.08 newtons and 1.15 seconds. So our final velocity is 1.27 meters per second. Okay. I am sorry about all the struggles there. Okay. Moving right along. We're now going to think about a fireman who is sliding down a pole. He's going from the top floor up here all the way down to the bottom. So there's our floor. Okay, so the fireman is going down. His weight is 70 or 97 kilograms, and he starts from rest and slides with constant acceleration. It tells us how fast it takes for him to reach the floor. We want to know the upward force exerted by the pole on the fireman. So the thing we are looking for is this force. We don't know what this is. Well, do we know what this force going down the pole is? Yes, we do. That force is going to be equal to the fireman's weight. And recall from the concept video that weight is just his mass multiplied by gravity. So let's just write out the things that we know. We know our initial velocity is 0. We know that delta x is negative 3 meters because this person is sliding down. And if you're not sure about that, here's our, we'll say he starts here at the origin and moves down. There's x, there's y. That's the coordinate system that makes the most sense to me. We know that the acceleration, a, is constant. And we know that t is 1.2 seconds. Okay. Well, we want to be able to use F equals ma. But in this case, we have multiple forces that are not equal. So we're going to have the sum of those forces, which is going to be equal, still going to be equal to the mass times the acceleration. Well, what are those forces? The forces are the weight and then this unknown force that we don't really know. So in order to solve for this, we are still going to need another piece of information. And just like in the previous problem, we will need to find the acceleration. So is there an equation of motion that allows us to do that fairly easily? Well, take a look at your chart. And I hope you can see that this equation of motion will be the easiest for us to use. And again, I'm writing y here because we are moving in the y direction. So I just went ahead and wrote y instead of x. Okay. I'm using this because I can cancel out multiple parts of it. We know our initial position is 0, and we know the initial velocity is 0. So this will just go to y equals 1/2 at squared. Well, lucky for us, we already know y, which is negative 3 meters. We have 1/2. We don't know a, but we know our time, which is 1.2. So when we solve for a, we'll find that the acceleration is negative 4.2 meters per second squared. And it is so easy to lose track of these negatives here. I catch myself doing it all the time. Negative 4.2 meters per second. Again, he's moving down in this direction, so that negative makes sense. Okay, now that we have acceleration, we can continue. And I'm going to erase more to make room for the next part. But I'm going to keep acceleration there because we'll need it in a minute. We mentioned earlier that the forces, so the sum of my forces, the things giving the total force, is going to be all of our forces happening in the y direction. Nothing's happening in the x direction, so we're just focusing on the y direction. And in this direction, we know that we have a force from weight, and we know that we have some other force, which we will just call F2. Okay, well, let's go back and start plugging in information that we know. I'm going to write this up here so I can move it out of the way. Okay, we know that the weight is coming down the pole. So we actually need to make this negative. And I'm going to start replacing these general forces with the information I know. So we know that weight is mass times gravity. And we know the second force, whatever that may be, is just ma. Okay, well, these both have mass in it, so we can just take mass out, and we get the sum is equal to m. I'm going to rearrange this, which would be, I'm sorry, I won't rearrange it, negative g plus a. And I can now begin plugging in my information. So when I actually plug in all of that information, I will find at the end, I'll actually do this part because I think you're going to get very confused if I don't. 97 kilograms. Okay, minus, well, gravity is in the downward position, so it's 9.81 meters per second squared, plus our acceleration, which is a negative 4.2 meters per second squared, equals 540 newtons, and this is in the y direction only. Oh no. We do not care about the x direction right now. Okay, so 540 newtons.